Welcome, everyone. So this is the last talk before lunch. I hope that you're all excited for the talk. And here we have Brian Goetz, Java Language Architect at Oracle, and talking about the Project Valhalla update. Please welcome Brian.
Thank you. So we're going to talk about Project Valhalla and the glorious future that awaits brave warriors who are proven to be deserving. Someone once called Valhalla Java's epic refactor. I don't remember exactly who coined this phrase, but it's a great phrase because it's the largest refactor of the language and runtime I think that we've ever undertaken. It's something that cuts through the entirety of the platform from the language, the libraries, the VM, the runtime, all the way down to the hardware. And it's something we've been working on for quite a long time, as some of you know. We've been working on Valhalla probably a little more than 10 years now. During that time, we've done a lot of experiments, explorations, analysis, many prototypes. And we finally, at this point, think we see the light at the end of the tunnel. And what we've been working on in Valhalla for the last few years has been the part where it faces the user, right? So the Valhalla is largely a refactoring of how Java programs interact with memory. This is a low-level thing, and is mostly the early phases and explorations were mostly hardware-facing. And we're now addressing the part where how is this reflected in the Java user model, the programming model, and in particular, if I have existing classes, how will they migrate forward into this Valhalla world? So I'm going to talk today more about the programming model aspects and a little bit less on the VM magic. One of the big challenges about a project like this is the motivation is performance. But we don't want to add performance features to the language. We don't want to have a go fast modifier because the history of such things have been almost universally failures. And so we want to let people write programs that express the semantics they want, that the VM can optimize effectively. So to talk a little bit about how objects get laid out in memory, recall that the JVM operates on two kinds of values, primitive values and object references. Not objects. Objects are sort of somewhere over there. We interact with objects through object references. And if you read the JVM spec, it says nothing about the layout of objects in memory. But if you read the JVM spec really carefully, you discover that there are a lot of constraints that essentially force us to lay out memory in a certain way. And so if we have code like this, where we have a point is an x and a y, and a rectangle is 2 points, we're essentially forced to lay it out like this, the way it was in the textbooks, the computer science textbooks that we learned from in the in the 80s, where you have a pointer to a rectangle. A rectangle has two fields, which are pointers to point objects. Each of those objects has an object header, and this is largely a forced move for a number of reasons. And there's nothing wrong with this layout, but it may not be as efficient as we like it to be. It's not very flat, which means that data is often on the other side of an indirection or a pointer. It's also not very dense. A lot of the memory that's used by this layout is used by overhead, like object headers and pointers, and not by actual data. And so this may or may not be a problem, but for some applications, it is a problem. And what's happened over the last 30 years is the relative cost of memory fetches versus arithmetic operations has diverged dramatically. So 30 years ago, a memory fetch and an arithmetic operation cost about the same. Now, arithmetic operations got much, much faster, memory operations got slower, and as a result, the costs have diverged quite a lot. And so, the question that we want to ask is, under what considerations could we make it possible for the JVM to lay out our rectangle like this, where the points and the XY value of the points are all flattened into a single object layout? We see a similar problem with arrays. If I say, give me an array of points, what I do is I get an array of references to points, or pointers. Each of those points to a point object. I know I'm saying point a lot. And a lot of our memory is tied up with object headers and pointers. And when I go to iterate my way through this array, every time I want to get some data, I'm at the other end of a memory indirection, which means I'm working against the hardware's natural optimizations for locality and prefetch. And in some cases, I would really rather my array of points be laid out like this, where I'm going to get good locality, I'm going to get good prefetch behavior. And so the questions that Valhalla is asking is, how do we make this possible? What are we asking the programmer to do in order to make this possible? And most importantly, can we do this without turning Java into C++? So to sort of understand the answers better, I want to talk a little bit about one of the problems that we inherited from the early days of Java. So you could say that Java's original sin is the divide between primitives and objects. And this was something that was essentially a forced move in 1995. It was the only way we knew how to do things so that we would actually get usably fast numerics. And it seemed kind of sensible, like numbers are special, int is a really special type, it's reasonable for, for the system to privilege it in that way. But it's kind of dogged us ever since, right? So like when you're programming and you have to use integer instead of int, we all feel a little bit dirty when we do that, right? And sometimes we're willing to distort our code a little bit to avoid that bad feeling. And so this is a pervasive source of friction in programming, both from a user psychology perspective, but also from a hardware performance perspective. And one of the nasty things that happens is if you have an architecture with a split down the middle, and then you try to build more things on top of that, each layer is going to inherit and sometimes amplify the split of the previous layer. So when we did generics, the rift between primitives and objects got worse. Generics, you could generify over all the types except for these 8 types. And you could, even if you could say array list of int instead of array list of integer, it wouldn't be backed by an int array, it would be backed by an object array. And then this got worse again with lambdas, with the explosion of hand-specialized types like intstream and int-to-long function. So, we inherited this rift between primitives and objects, and the interest on this debt has just grown over time. So it feels like it's time to unify these things. But that's a hard job because primitives and objects differ in almost every conceivable way. One's built in, one's user defined. One has members and supertypes, the other doesn't. One has identity, the other doesn't. One is nullable, the other isn't. One is polymorphic, the other isn't. The differences go on and on. I mean, they're different in almost every conceivable way. So if you're crazy enough, like me, to say, well, why don't we unify these under one concept? There's a lot of work to do. But it's work we have to do because the interest on this, on this architectural debt that we inherited is really getting to be quite severe. And in some sense, we don't need primitives. We can do everything we want with classes. The main reason that we had these things in the first place is that primitives came with a built-in density and flatness advantage. And so because primitives are special, developers find themselves facing a bad choice. They could either write clear, clean, object-oriented code, or they could choose efficiency and do it with primitives and end up with less maintainable code. And we know that people often make the wrong choice in that situation. Similarly, we have the primitives we have 8 primitive types, and it's very difficult to add more because of the way primitives are implemented. But there are lots of other numeric types that we would like to have in our language, like decimal or 16-bit floats or complex numbers, et cetera. And we would like for those things not to look bolted on the side. We would like to be able to gracefully grow the language without seeing this big rift between these are the built-in things and these are the things that were added on the side. So with that as background, the goals for Project Valhalla are threefold. One, enable flatter and denser memory layouts for Java object graphs so that Java's programming model is more aligned with the performance model of today's hardware. Unify the type system, so heal the rift between primitives and objects, and enable new numeric types to be added to, as libraries, not as built-in language features. And ideally, this gives developers the best of both worlds, the abstractive power of classes and the runtime characteristics of primitives. And so our slogan for this is, codes like a class, works like an int. Now, this is not a trivial problem. There's lots of hard problems in here. We've done lots of good work in the last, in the last years. But by far the hardest aspect of this is, how do we integrate this into the language so it doesn't look bolted on the side? And how do we make it so that code that was written before Valhalla will migrate gracefully to a world with Valhalla? So some of you may have seen the keynote that I did at Devoxx this past November called Postcards from the Peak of Complexity. And one of the things that I've observed from having done several of these decade-scale language evolution projects is that they actually have a common life cycle, and they go through a predictable set of phases. So it always starts with some completely unwarranted optimism. Oh, we could do this amazing thing, it'll be great. And then reality sets in. And you think, what idiot signed us up for this? Then begins a long, slow climb to what I call the peak of complexity, where you chip away at the problem little by little, and you have a, sort of a list of like, well, we haven't solved this yet, we haven't solved that yet, and little by little, you check those things off the list till you get to the point where you have a solution. Right? And this is the dangerous part of the project, right? Because you think you might be done. You really want to be done. Your manager wants you to be done. Your users want you to be done. You're not done. And if you make the mistake of shipping this, you are hopelessly screwed, because you're going to be playing catch up for the rest of your career, because you will have shipped an overly complex solution, and then the only way to fix an overly complex solution is with more complexity. Now, if you have the latitude and discipline and management support to move a little bit more slowly, you have the opportunity to steer towards what I call the virtuous collapse, where you look at this Frankenstein monster that you've created and you start to imagine, well, maybe we don't need all the parts of this. Maybe we didn't understand the requirements quite right, and we can let go of this little bit. And if we can let go of that bit, then we don't need this other bit. And this thing, we thought it was consistent with the design, but really it was just an opportunistic add-on. We can get rid of that. And if you're really lucky, the complexity just boils away, and you are left standing looking at it and say, wow, where did it all go? Now, I don't mean to suggest that every project is going to go through this or that this is easy, but it is really beautiful when it happens. And if you get there, then you are lucky enough to get to the point where everybody says, what took you idiots so long? I could have told you that answer 10 years ago. So that's where I'm kind of hoping we are. So you can tell me if you agree. So flatness and density, what are the impediments? Well, we started out thinking that the main impediment was identity, that object identity forces objects to live in a single place at a time, and that forces the memory layout that we have. And object identity is great for some things. We need it for some things, like mutability, but not all objects need it. And maybe if we let identity be optional, we would achieve the flatness and density goals that we want. And then it turns out that that was an important part of the answer, but it wasn't the whole answer. We started to realize that nullity was also a significant part of the answer, both from a flatness and density perspective. But if you think about it, a long uses all of its 2 to the 64 bit patterns. So if you want to represent nullable long, you need at least one more bit. So that's 65 bits, and that's really 128 bits on modern hardware. And so nullity or nullability is a density problem, which also, for surprising reasons, turns into a flatness problem. And then we thought, okay, it's identity and nullity. It's starting to sound like a Spanish Inquisition sketch, right? The impediments to flattening are object identity, nullity, initialization. It sort of went on. But there are other impediments as well that we were chipping away at as we were climbing to the peak of complexity. So let's talk about these in turn. We always knew object identity was flattening enemy number one. Every object has a unique identity, and when you compare two objects with the equal operator, it's asking, do these two object references, not objects, because we only get to deal with references, do these references refer to the same object, where same object means has the same identity? And we have object identity because we need that for mutability, we need it for layout polymorphism, and then we sort of opportunistically glommed on a bunch of other things onto it, like intrinsic monitors and locks. And a lot of classes use these, but a lot of classes don't. Many, like domain model classes, numeric classes, don't need them. They don't use any of these things. They're final classes with final fields that don't need their object monitor. And in fact, like in classes that don't need object identity, having it is often a source of bugs. How many people here have been bitten by the fact that like small capital I integers are equal to each other, but large ones aren't because of the box cache, right? And this is an example of, equal equals is asking a question about integers that no one should really ask. Two copies of the number 42 are the same number, even if they exist in separate heap nodes. And object identity is a problem because it basically forces that an object live in one authoritative place so that if you're going to update it, you know where to make the updates. So this identity virtually forces the layout that we have, unless we're lucky and we can prove that the object doesn't escape and it's not aliased, and we can do VM heroics like escape analysis. So this was flattening enemy number one, and so our solution to that is, if it's a problem and you don't always need it, let people opt out of it. So a value class is a class whose instances do not have an identity. They're just their data. This means you give up some flexibility, like mutability, but it also enables the VM to optimize these objects much more effectively. Now, it's important to note that when I say this is a value class, this has nothing to do with performance. It's a purely semantic statement about whether these instances have identity or not. And we've all written classes that are logically value classes. There's a lot of them in the JDK, like integer and long, like local date, like optional, most tuple classes, things like that. These are logically values. We'd like to be able to make them actual values. So to declare a class as a value class, all you do is put the value modifier on it. It means the fields are final. It means the class is final. And there are a small number of changes. So value classes differ from identity classes only in a few ways. Like I said, implicit finality for the field in the class. Equality compares value objects based on their content, not on their identity. So two integers are equal if they describe the same integer. And so that we don't care if they've been allocated separately on the heap. If they both have a 42 in them, they're the same number. They have no lock, so you can't synchronize on them. Similarly, you can't use them with things like weak reference. But otherwise, they're pretty much the same as identity classes. They can have supertypes, they can have constructors and fields and methods and generics, and all the things that classes can have. The important thing to note, and this took us a while to realize, is that they're still objects, and they're still referred to by object references just like any other. So we haven't changed the model of there are primitives and there are object references, but what value types let us do, or let the VM do, is optimize away the physical representation of the object reference, which is the pointer, and potentially inline the layout of value objects into their enclosing class. And this is enabled by the lack of identity, but that means that I can freely copy, copy a value object state. I can shred it into its fields. I can hoist those fields into registers, and then I can reconstruct the object, and no one can ever tell the difference. And this is what enables all of these optimizations, such as calling convention optimization, local usage optimization, and heap-based flattening. So the cool thing is, we've all if you look at a loop where you're accumulating a value with an immutable counter, like an integer, we all look at that and cringe and say, oh my God, think of all the allocation. Well, you can write that code today and there's no allocation. It all folds away. It's just as fast as the mutable code. So you can get the performance of mutability with the safety of immutability. So a couple of examples. If you pass a value object between methods, either passing it to a method or returning it from a method, What we do today is we put the object on the heap and we pass a pointer. But with value objects, we have an optimized calling convention where the object doesn't ever have to get allocated. We just hoist the fields into registers and we pass them that way. So here's an example where we're returning a point from a method, and the new keyword here is a little bit deceptive because we're all trained to think that the new keyword means malloc, allocate something on the heap. What it really means is make me an object, I don't care where. Historically, most of the objects have been forced to be on the heap, but value objects don't have to be on the heap. So if I say, make a new point and return it, what's going to happen is the VM's going to say, I don't need to allocate anything on the heap. I'm just going to hoist the X and Y field into registers and just return those. And so this is a significant optimization for method calls, completely separate from the heap flattening that I illustrated in the earlier box and pointer diagrams. Similarly, if I'm looping over a collection of things and I want to accumulate accumulate something, historically, if I did this with an integer, I would allocate a new integer every iteration through the loop. But again, we're going to migrate integer to be a value object, and the VM's going to look at this and say, well, I don't actually need the box. I just need the thing that's inside it, which is an int value, so that'll start out at 0. I'll go over my loop. Each iteration through the loop, I'm going to add something to it. No allocation. So, this is really the goal, is to let us program with the safety and abstraction that object orientation gives us, lean on immutability because immutability makes our program safer, and then have the VM erase all of that and just give us something that looks like the handwritten assembly code that we would have written if we really cared to do so. So this is pretty cool. So we're delivering in stages. The first JEP is JEP 401, which delivers a piece of the Valhalla story. You can think of it as the groundwork, which is value classes only. So one new keyword, value, you can put it on classes, that's the only syntactic change. We're going to migrate some of the classes in the JDK to be values like integer and optional and local date. And like I said, to start, the focus is on semantics and some of the basic optimizations like the one that I've described. There's more flattening coming, but that's coming in future JEPs. So we get some semantic benefits, some performance improvements now, more performance improvements later. The advantage of this approach is there's relatively little new complexity to absorb right now. Basically, when you're writing a class, you should ask yourself the question, does this class need its identity? If it doesn't need its identity, don't have it, right? And this is this is something that we're used to doing as programmers, right? Does this field need to be mutable? No, make it final, right? Does this class need to have identity? No, make it a value class. So I mentioned that identity was not the only impediment to flattening. Another is nullability. And this is because null is an extra value that we have to encode in object references, and we want to flatten away the object references so they don't happen. So nullability is a flatness hazard and a density hazard. So sometimes nullability is really useful. Sometimes it's not useful. The existing primitives that we have are not nullable. They're not nullable for a reason. Most numerics code doesn't need null, doesn't want to pay for null, and finds null to be an impediment. It gets in the way. That's why primitives, we're not nullable. And like identity, nullability is something that we might want to opt out of when we don't need it, so we're not paying for the overhead of it. And so, just like identity, if we don't need it and it's not wanted, and it gets in the way and it creates overhead, let's make it optional, let people opt out. Now, if you've programmed in Scala or Kotlin or C#, you've seen types like string bang and string question that mean non-nullable string or explicitly nullable string. This is a concept that developers have asked for in Java for a long time because it makes sense. People complain about null, but really what they hate about null is not null itself. It's that something that you think is non-null might be null, and you have no way to express that you don't want it to be null. And so nulls can creep in and surprise us. And that's what people really don't like about it. The notation, the bang and question mark notation, did not originate with Scala or Kotlin or any of the languages that most of us have seen this in. It was largely explored in an experiment that Microsoft did called X#, or later renamed to C omega, which borrowed these from regular expressions because they represent cardinalities. Those experiments had cardinalities not only for exactly 1 or 0 or 1, but also 1 or more or 0 or more. This was simplified by the languages that adopt this as like, oh, well, we really only care about the 0 or 1 case, and so we'll leave the other cardinalities out. Null restriction is not a small feature. There's a reason why we haven't done it already, but it is something that people want separately from Valhalla, and it's also important for Valhalla. Now, we tried a failed experiment in the early parts of Valhalla to make value types non-nullable by default, which felt like locally a good move, but it turned out to make migration of classes to value classes even more difficult. And so it was sort of a good lesson that like the things that you do locally to optimize things often turn into impediments to global optimization. Unfortunately, identity and nullity are not the only challenges we have. So we can enforce, for example, in the VM that if we say that a given field is a non-nullable string, we can, we can reject an attempt to write a null value to it. But what about initialization? What's the initial value of a field whose type is something like string? Null, right? Well, that's really bad because the initial value is not even in the value set of the type that you declared in your program. And unfortunately, it is possible to see the initial value of fields before they get initialized. And we didn't want to have invalid values leaking out. And so we had to do a little bit more work to upgrade the definite assignment rules, both in the language and in the VM, to ensure that if you have a null restricted field, you can't read it until it's initialized. And similarly, we have a problem like that with arrays, right? If we allocate an array of non-nullable string, what's the VM going to want to fill it with? Nulls. We don't want that array to escape because we've said, hey, this array is full of non-null values, except that it's full of nulls, right? That's a dirty trick to play on people. And so we will need some sort of better array initialization idiom where we say, make me an array of non-null strings, and here's a value to put in all the fields, or here's a lambda to run to populate all of the elements. And so initialization is also a part of the flatness story. So this will play out over 2 more JEPs. The first simply is adding null restricted types to the SIPE system and does all the work of threading that through all the various parts of the language, type inference, bounds conformance, method overload selection, pattern matching, etc. And we can enforce this dynamically. The VM can enforce that you don't put nulls where they don't belong. We can enforce them at separate compilation boundaries so that if we've migrated one class but we haven't migrated its callers, for example, and they try to pass a null, we can reject that at the boundary. And some additional new rules for, like I said, making sure that these things don't go uninitialized. Now, the type system that we end up with at the end of this exercise is slightly different from what you might expect if you've seen null restricted types in Scala or Kotlin or C#. And that reflects the fact that we care in the Java community tremendously about compatibility. So if we give people the ability to say, take an existing API, and now, great, you can add bangs to say, don't pass a null to me, that's great, you've improved the API. As long as that's a compatible move. If that were not a compatible move, then no one would ever do it. And that would kind of defeat the purpose. And so we end up with slightly different set of rules that you might expect in order to support the goal of migration compatibility. This problem gets worse when you consider null restricted value types, because value types are objects, and objects have invariants. Those invariants are protected by the constructor. There are certain instances that are not valid, and the constructor is what guards you against creating, creating invalid instances. But if we flatten objects into their enclosing layouts, we have to make sure that we don't expose a flattened object before its constructor has run. And that's because while some classes have a reasonable default value, like integer, 0 is a totally reasonable default, some classes do not have a reasonable default value, like date. The traditional default value for date is January 1st, 1970, which is a terrible default value, as is January 2nd, 1970, and all the other dates, right? There is no good default value. It's having a default value for a date is just a bug generator. And so for classes that have no good default, we have to be very careful to make sure that we cannot expose one of these before they get initialized. So this is one of the challenges that happens when you mix null restricted types and flattened value types that you don't have, when you only have one of those things. And so, we have a story for this too. This is largely the same story as before. We have to beef up definite assignment and ensure that the fields of value types and the state of null restricted references are initialized before they're used. So this is leaning on an existing mechanism in the language, definite assignment, and just strengthening the stories about when it's used. There's a separate activity that you might have seen. There's a JEP called flexible constructor bodies, which allows you to put statements before the supercall in a constructor. We leaned on that very heavily. There are certain things that you have to put before the supercall, because once you make the supercall, your object state may be exposed to code that you don't control. So if you sort of add all this together, if you look at the prototype that we have that supports all of these features, you see some pretty dramatic improvements in performance, which come from a combination of places: scalarization, optimized calling convention, increased locality, decreased allocation, decreased garbage collection. And for things that are using large collections of numerics, like multiplying matrices or summarizing collections, we see some pretty dramatic throughput numbers, 6x, 3x, 12x, 8x in various situations. But one of the really nice things that comes out of this is the gap between using mutable state and using immutable state closes dramatically. So these are very nice validations of the work we're doing, but this is a consequence not of having used performance features in our language, but by having given up semantics that we don't need, so the VM can more effectively optimize our program. Now, some of you may remember back in the bad old days, in the Java 1.0 days, there were these really scary warnings in the JLS about if you used 64-bit primitives like longs and doubles in concurrent programs, it's possible to see them tear, where you'll get the low 32 bits of one operation and the high 32 bits of another. Does anybody remember these scary stories that we told to children at bedtime to get them to behave? Okay, so this was something that was essentially another forced move given the hardware of the time, but the hardware improved very quickly, and eventually we didn't have to worry about this in practice because the implementations were able to use fast 64-bit atomics that came along a few years after Java was invented. But this is kind of a dark story from our past, where we tolerated seemingly dramatic bit of unsafety in the language, where where you could get garbage values that weren't put into a variable by any thread. And why did we tolerate this? Well, it was a combination of things. One is numerics had to be fast, otherwise no one would use Java. Concurrent numeric code was rare, and this only happened in concurrent code. In fact, it only happened in broken concurrent code. And so you were able to say, well, yeah, that's a bad result, but yeah, your program's broken, so we're going to err on the side of performance rather than avoiding a surprising result in an already broken program. I say that very glibly. It was a complex trade-off at the time. I'm sure it was argued extensively. And we don't have to worry about that now, right? Because we have efficient 64-bit atomics. unfortunately, that's not true, because value types will allow us to declare value objects that are bigger than 64 bits, and we still don't yet have efficient 128-bit atomics, and it's not clear we're going to for quite some time. And so this old problem that we didn't have to deal with now comes back to bite us, where we have to worry about the possibility of tearing for large value objects if we flatten them, if they're accessed concurrently under data race. So this is an area still under investigation about what the proper programming model is, but we think that this is a little bit different from what we saw with longs and doubles, because value objects are classes, and classes can have invariants, and we kind of expect that the invariants that are enforced by the constructor will stay in place through the lifetime of an immutable object, right? That sounds reasonable. So for value objects over 64 bits, the flattening story is still to be written. And there's definitely no one-size-fits-all answer, so we're going to have to get some additional guidance from the programmer on this. We're pretty sure the default is going to be safety over performance, but there will be a way to hint which way you'd rather go in these situations. One of the nice things is, so value objects are immutable, but you can have immutable references to value objects. And in the examples I gave about accumulating into an integer, we had exactly that. All of the problems I just described on the previous slide only happen when you have a mutable reference to a value type. If you have an immutable reference to a value object, no problem, we can flatten this basically all the time. So, the conditions under which the VM can give you optimal flattening are complicated. We're hoping that people are not going to try excessively to reason about this, but instead focus on the cases where it matters the most, where you have big arrays of numbers and things like that. So just to sort of give you an idea of the kind of flattening that we expect over time, from the beginning, we expect to see excellent flattening in calling convention and in local usage, regardless of object size within limits. I mean, if you have an object with 10,000 fields, we're not going to pass the values in registers. We're just going to put it on the heap and pass a pointer. On the heap, for small nullable value types, we can still flatten them if there's room for a null bit. With non-nullable value types, we can flatten those to a slightly bigger size. And larger values can be flattened if they're final all the way up, or if we opt into some kind of relaxed atomicity whose story is to be written. And if the hardware ever gets better, like it did when we went from 32 to 64 bits, the threshold at which we have to worry about this will go up accordingly. So I've only shown you two language features, value classes and the ability to restrict nulls. And that seems like a pretty simple programming model. So what took you 10 years? We didn't realize it was this simple because we had to go through the process of doing it wrong a bunch of different ways to figure that out. But we had a philosophy that stood us in good stead, which is that flattening should be purely a JVM optimization. We should focus on writing our programs with the semantics that we want. We should give people the ability to disavow degrees of freedom that they don't need so that the VM can optimize more effectively. And certainly the history of performance-oriented features like the register keyword in C is not encouraging, and we wanted to avoid things like that. So the challenge is, well, okay, we know what the wrong levers are, register keyword. What are the right levers? Well, we found a bunch of wrong levers along the way until we found the right levers that let us say what we want in a way that the VM can reward us with the performance that we want. But our best trick is one that we've had for a long time, which is opting out of unneeded degrees of freedom. Somewhat surprisingly, but shouldn't have been surprising, was that by having clean and uniform semantics, things like migration compatibility kind of fall out along the way. We knew from the beginning that migration compatibility was going to be essential because people have written some Java code already, and they'd like for that Java code to not, to be able to move forward into the new world. So it would be terrible if we added value classes to the language, but couldn't migrate classes like integer and optional and local date. And it would be terrible to add non-nullable types to Java and not be able to refine the signatures of the libraries that we already have. And many of the earlier design iterations, their defects showed up in the form of a lack of migration compatibility. And these were kind of a warning that we hadn't fully integrated things into the model. And once we cleaned up the underlying problems, these things kind of just fell out, except, of course, for serialization. So serialization is the tax on every language feature that we develop. There's always some horrid interaction with serialization. And if you think about how serialization works, well, it makes a blank object and then pokes values into it. But value objects are immutable, and there's no way to allocate a blank object. And so the mechanics of the existing serialization are kind of at odds with the nature of value classes. This, fortunately, was something that was amenable to re-implementation work in the serialization stack. And we're working on the problems of serialization separately, which I'm not talking about at this conference, but there's a talk that Victor Klang and I did at Devox this past November about what we're doing about serialization. So this is something that is one of the many reasons why this took longer than you might have expected, because there are interactions with legacy features like serialization. So it's kind of surprising, though, that modulo the stuff that I talked about that we haven't finished yet and the serialization work, that there really isn't very much to this new programming model, or so it seems, right? And the way it shook out, which kind of seems obvious in hindsight, is that for each impediment to flattening, they map to a single language feature. Identity was an impediment, opt out of identity with value classes. Nullability was an impediment, opt out with non-nullable variables. And of course, the language surface is simple, but the implementation goes all the way down to the metal, and that was not, that may not have been a simple implementation task, but the deal that we offer developers is a simple one, which is opt out of the degrees of freedom you don't need, and the VM will reward you with the best performance it can. As the complexity, sort of dissolved away when we had found the correct model, there was also kind of a nice side benefit that we weren't prepared for, which is there were a number of features along the way where we said, boy, it would be really nice if we could do this. No, we're never going to be able to do that. And all of a sudden, oh, we can do all these things. And it's really a testament to the power of having found the right model, because many of these, many of these things that we would have liked to have done but thought we couldn't was because we were working with a model where we hadn't solved the problem at the right level. Similarly, if you track the impact on the JVM spec over the years we've been working on it, the first edition was amazingly intrusive into the JVM spec. We had new bytecodes, we had new type descriptors, we had new verification rules. It was deeply intrusive. And if you look at the change to the VM spec today, it's a few new bits, no new constant pool forms, no new bytecodes, no new type descriptors, a few new verifier rules, but relatively minimal, which is pleasant and surprising. But still big implementation changes. So, like I said, this seems so simple, easy to ask, what took you so long, right? So I expect that. But you have to get it wrong before you get it right. Initially we thought, well, let's simplify the problem by not solving this part in the VM. We'll just try to solve it in the compiler. And that created gaps that we just had to paper over. And so just deciding what if this is a language feature versus what if it is a VM feature was a big part of finding the right problem. And the business about the interaction with the flexible constructor bodies JEP was almost seemed by luck, that we were designing this thing as a convenience feature, and we realized, oh, we can piggyback initialization safety on that, and no one will see it. Which, we might have figured out eventually, but it was kind of a lucky accident. But lest you think we were just sitting around all this time, I asked some folks on the team to kind of make a list of the significant investigations we did as part of this project before we came up with the final answer, and I could talk for an hour or more on any of these things, right? These were deep explorations, experiments, some of them multi-year prototypes that informed what the right answer would be. So to get the right answer, you have to visit a lot of wrong answers. So I've talked about 4 JEPs, value objects, null restricted types, null restricted value types, and there's a 4th JEP here, JEP 402, that's kind of a mop-up of some of the gaps between existing primitives and value classes. If we make integer a value class, we'd kind of like the primitive int to be basically the same type as integer bang, because they have no semantic difference. We can eliminate about 98% of the differences. There's still going to be a few that we're not going to be able to, get away with, mostly having to do with special rules and overload selection that was designed to preserve migration compatibility when we did generics and autoboxing. But for the most part, we can make int arrays covariant with integer bang arrays. We can deal with the fact that primitives can't be used as type arguments. We can deal with the fact that you can't override integer with int, things like that. So there's a sort of cleanup JEP that will file down these rough edges, but there's a lot more work after that. So if we're adding new numeric types to the platform, it's almost an immediate question to say, well, where's my operator overloading? And yes, we know. And we know this is a big area. We know this is an area where other languages have hatched serious disasters. So we're going to proceed carefully with this. We have some plans, which I'm not really going to talk about because they're so cool that that's all everyone will ever want to talk about. So we're going to focus on delivering what we've talked about so far, and then we can, address the follow-on work. Similarly, what about reified generics? Right now, as Valhalla, stands, we can flatten value types into the layout of enclosing objects, but if generics are erased, we can't flatten generic types that are instantiated with value types yet. And designing, a compatible reification scheme for specialized generics is a very, very difficult problem. It's something that's actually been on a slow burn for the last 10 years. Obviously, migration compatibility is just as critical now as it was when we did generics the first time around. There's an initial design draft about this called the parametric VM. You'll read it and you'll say, oh my God, this looks like a complete spec, but it's a draft. And it's something that we will turn to when we finish the JEPs that are in progress. So just summing up, the last 2 years have been a huge turnaround in this project because we've been finally able to face the challenges of how Valhalla interacts with the user and not just how it interacts with the hardware. The intrusion into the language and the VM is surprisingly small, although there's still a lot of complexity. And we have a phased delivery plan where JEP 401 is well underway. The spec's been stable for over a year. It's just a simple matter of implementation. And some of the VM engineers are in the room here, and I can hear them rolling their eyes. So, and then there's some follow-on JEPs as I described. So do we have a few minutes for questions? I think we have like 2 minutes or so. Okay, so question over here. Yeah.
So you showed pretty impressive performance gains, but that is without. So there they use the arrays. And in real-life scenarios, we usually use generics. So my question is, how much of a performance impact you expect in real-life scenarios where we have many generic code before we get to the specialization?
Yeah, so the question is, okay, great performance numbers, but what about with generics? And the answer is, you're not going to get those great numbers if you have arrays of generics. But if you look at numerically intense code today, big data analytics, machine learning, a lot of those work with primitives already and big arrays of primitives already because those are the types that are flattened already in the VM. And so you could look at this as glass half full or glass half empty. All of those examples can use classes now instead of primitives, but they can't yet use generic classes now. So glass half full, glass half empty. Maybe one more question?
get a compilation error or a runtime error?
Yeah, so the question is, I stick value on a, on a class that doesn't meet the requirements to be a value type. Is this a static error or a dynamic error? Yes. So there are a lot of obvious things that we can detect statically, right? So if you have a synchronized method, that means you're using the class's intrinsic object monitor, and there is no intrinsic object monitor. The compiler will reject that. If you try to subclass that class, well, it's final. The compiler will reject that. So there's a lot of static type checking, but there's also some dynamic type checking. So if you take a reference to a value object, you cast it to object, and then you synchronize on that. Well, the compiler can't tell that the thing behind the synchronized is doesn't have an identity. So the compiler will let that through, and then you'll get a dynamic error. So we try very hard to check what we can check with the static type system, but the static type system is not the same as the dynamic type system, and there are some things that get checked at runtime. All right, I think that covers the time. Yeah. So thank you very much.
Thanks a lot, Brian.